Greetings, Mr. Sutton here with the AB Calculus 2.8 Extra Practice Number 2 solutions on rate of change.
For this free response problem, we're given this graph of f, and we're told that we have a vertical asymptote at x equals -2. Good to know. We've also got a continuous function g, and some of the x values are represented in this table here, and they tell us it's an increasing function for all x. Okay, so first task on this free response, using the graph of f and table for g, we want to estimate limit as x approaches 1 of 2f of x plus 3g of x. So first thing we can do, since we're taking a limit of a sum, we can actually split this up, and we can also bring this 2 and this 3 outside the limit for whatever that's worth. So we can rewrite this as 2 times the limit as x approaches 1 of f of x plus 3 times limit as x approaches 1 of g of x, like so. And now that we've rewritten it like this, we can do a little estimation. So the limit as x approaches 1 of f of x, for that we're going to look at the table, and the graph rather. In the graph, as I approach the x value 1 from the left and the right side, it looks like in both cases I'm heading toward the y value 4. So I can rewrite this first expression as 2 times 4, and I'm going to write approximately equals, because we are estimating here, at least with this table we're going to be estimating. On the graph, it looks pretty clear where we're going. But now let's look at the table, because if you want to figure out the limit as x approaches 1 of g, we're never going to know what it is exactly, but we can estimate based off of this table. As x approaches 1 from both the left and the right side, it looks like the y values are trending toward 5. So we're going to go with 5 for this one. We're going to say 3 times 5. And we're at least guaranteed that the limit is somewhere between 4.996 and 5.004, because they told us that g was both continuous and increasing. So we know that at the very least we're going through 5, and it's going to happen in this interval here. So if we wanted to, we could simplify this a little bit. We've got 8 plus 15 giving us a total of 23.
On this part of the problem, for each of the values -2, 2, and 3, we want to figure out if f is continuous or not at these different x values, and use the definition of continuity to justify the answer. So definition of continuity says that if your limit exists, your function value exists, and they equal each other, you are continuous at a specific x value. So with that in mind, let's take a look at each value. -2, let's start with that one. So at -2, that's where the vertical asymptote is. So at that value, both f of 2 and the limit as x approaches 2 are both non-defined, do not exist. So therefore, by the definition of continuity, this function is not continuous at x equals -2. Moving on to +2, at +2, the function value is 4. The limit from the left and the right is also 4, so these two things equal each other, and they both equal 4. Since they both exist and they equal each other, therefore we would say f is continuous at x equals 2. And then finally, for x equals 3, right here at this removable discontinuity, the function does not exist there. Therefore, since f of 3 does not exist, this function is not continuous at that x value. On this problem, we're trying to find the limit as x approaches 0 of f of x. So with composition of functions, you have to do the inner limit first and then work your way out. So we're going to do left versus right limit. So we're going to first evaluate the limit as x approaches 0 from the left, and we'll start by doing the inner f of x function. Now, inner f of x and outer f of x, they basically do the same thing. You're using this graph for both of them. But the key to this problem is realizing that the output from this inner f of x function is going to give you the input to the limit of the outer function. So let's see how this plays out with the left side limit at 0. As x approaches 0 from the left side, so coming from the left side here towards 0, we get an output for that inner f of x function of 1. We're going to 1 from the left side there. Now this 1, that's the output from the inner function, this is actually going to be the input for the outer f of x function. So when I try to take limit as x approaches 0 from the left overall of this whole thing, what I'm really doing is taking this outer f of x function and approaching 1. And since I was approaching an output value from above to get this 1, that means I'm approaching 1 from the right side, from the more positive side, for this outer function. So I go back to my graph now, and now I'm looking at the limit as x approaches 1, which is right here, from the right side. And that brings me to this removable discontinuity, which has a value of 4 for the y value. Okay, so to recap, because we're going to do this again, find the inner limit using the inner f of x function. That gives you the input for the outer limit, and you have to pay attention to which side, above or below, you found that inner limit from. So let's do this again now, approaching 0 from the right side. So as I approach the inner f of x 0 from the right side, so starting here, I'm just going from the right side towards 0, that gives me a y value, an output of 2. Now again, this output from the inner f function, that output is the input of the outer function. So approaching 0 from the right side for the whole function f of x, this is really equivalent to the outer f of x function approaching 2. Since we approach 2 from above, that means we're approaching 2 from the right side when we actually look at this from the perspective of the outer function. So going back to the graph, we're approaching 2 here from the right side, and that is bringing us to a value of 4. Now, this 4 and this 4, they're in different places on the graph, but when you're doing limits, the only rule is if the left and the right agree on the number, regardless of how they got there, then your limit exists. Well, the left and the right limits are the same. They're both 4. So therefore, the overall two-sided limit as x approaches 0 of f of x is going to just be 4. For this last part of the problem, they want us to write a difference quotient that best approximates the instantaneous rate of change of g at x equals 1. So this is really not too hard if you understand what they're asking for. A difference quotient is essentially something minus something over something else minus something else. In this case, since we're trying to approximate an instantaneous rate of change, we're going to do that with an average rate of change. Now they said best approximates. So we're going to do an average rate of change over the smallest possible interval that contains x equals 1. That would be the interval from 0.999 to 1.001. So we're just basically going to do y2 minus y1 over x2 minus x1, or 5.004 minus 4.996 over 1.001 minus 0.999. And notice that I said g prime of 1 is approximately equal to this. We know it's not exactly equal. We're signaling to the reader that, hey, this is just an estimate. Truth in advertising. On this problem, a function and its derivative are given in this table here, and based off this table, we want to do the following. So first task, we want to find the slope of the secant line over the interval from 4 to 15. So for this, we need basically to use the slope formula. We need to do f of 15 minus f of 4, basically y2 minus y1, over 15 minus 4. F of 15 in our table is negative 10. F of 4 is 45, so we've got negative 10 minus 45 over 15 minus 4. This is negative 55 over 11, which we could reduce if we wanted to negative 5. So that's the slope of our secant line. Now to write the equation of the secant line, we're going to use this slope, and we're going to use a y value and an x value. So in general, we're going to use point slope formula, y minus y1 equals m times x minus x1. And our slope that we're using is negative 5. That's the slope of the secant line that we just found up here. For the x and the y value, we could use either 4 or 15 as your x value, but you got to commit. Once you pick one of these, you have to pick the y value that goes with it. So if I pick an x value of 4, then my y value is going to be f of 4, which we already saw in the table was 45. So I've got y minus y1, which is going to be y minus that 45 that I just looked up. My slope was negative 5, and then I have x minus the x value that I just plugged in, which was 4. And this is one possible equation of the slope of the secant line here. Now, another way you could have written this, if you use the x value 15, you could have written this as x minus 15 and y minus negative 10, depending on how you wanted to go with this table. For the next part of this problem, using the same table from parts A and B, they want us to find the slope of the tangent line at x equals 11. So another word for slope of the tangent line is the derivative of the function at x equals 11, so f prime in other words. So basically, all they're really asking for on this problem is just f prime of 11, which we can look up in the table. At 11 for the x value, the f prime value is clearly 50. All right, well, that wasn't so bad. Next thing they want is the equation of the tangent line at x equals 11. So for this, we are again going to use point slope, y minus y1 equals m times x minus x1. And I need a y value to go with my x value of 11. So the y value would be f of 11. Looking that up in the table, that looks to be 1. So plugging it all in, we've got y minus the y value 1 equals m. That's the slope of the tangent line that we found in part C, so that was 50. And then we'll have x minus the x value we plugged in, which was 11. So there's the equation of your tangent line. For the equation of the normal line, we're basically using the tangent line, but we're going to use the opposite reciprocal slope because the normal line is perpendicular to the tangent line. So we still have y minus 1. We're still going through the same point, but now instead of 50, we're going to have negative 1 over 50, opposite reciprocal. And then we will still have x minus 11. For this problem, we're given this polynomial, and we want to write an expression for the instantaneous rate of change at x equals 3. So I'll start by writing the IROC formula out, Newton's version of it. Limit as h approaches 0 of f of x plus h minus f of x over h. And now I've got an x value of 3 that I'm going to have to plug in. I also have to replace all of these x terms with x plus h's and just x's, I guess, because I've got two different versions of this function. So let's start by applying this f of x plus h. So I'm going to be plugging x plus h in for x, but now x has a value of 3. They said x is 3. So I'm going to be replacing all of the x's in here with 3 plus h's. So instead of writing x squared, I'm going to write 3 plus h squared. Instead of writing 3x, I'm going to write 3 times 3 plus h. And then minus 2 is still playing itself in this motion picture. That hasn't changed. So that was f of x plus h, or f of 3 plus h in this case. Next, we're subtracting f of x, which in this case really means we're subtracting f of 3. So we're going to have 3 squared plus 3 times 3 minus 2, all of that. And I'm going to subtract all of that in a parentheses because it's all being subtracted, so we don't want to lose anything. And this is it. No need to simplify it. Good the way it is. On this one, we have a rock being dropped from a height of 576 feet, falling toward the earth in a straight line. T seconds, the rock drops a distance of 16t squared. There we go. We want an expression for the instantaneous velocity, which is the rate of change of distance, at 6 seconds. So basically, we want instantaneous rate of change of 16t squared at t equals 6. Let me start, since this is an IROC problem, by writing out Newton's instantaneous rate of change formula. So that's limit as h approaches 0 of, we're going to have f of, I guess in this case we're going to have t plus h plus minus f of t all over h, although I guess you could call it x in general. It doesn't really matter what your input variable looks like. So in this case, we have an x value, or in this case, I guess a t value of 6. So we have 6 plus h and 6 in here. And we're applying the 16t squared function. So I can rewrite this as 16 times 6 plus h squared minus, and now we're just doing 6 for t, so 16 times 6 squared, all over h as h approaches 0 limit. And here's our instantaneous velocity expression.
On this problem, we want an expression for the tangent line slope in terms of x for this function. So let me start by writing the equation for a tangent line slope, just the general IROC formula. Limit as h approaches 0 of f of x plus h minus f of x over h. We don't really get anything for just writing a general formula, but it's nice to know where I'm putting everything. So I basically have to apply x plus h to this function here. So instead of writing 2x squared minus 1, I'm going to write 2 parentheses x plus h squared minus 1. And I'm also going to be subtracting just f of x, which is just all of this stuff with x in it right here. So this is everything I need for the tangent line slope in terms of x. On this problem, they want an expression for the derivative of this function here. So I'm going to start with Newton's general derivative formula. Limit as h approaches 0 of f of x plus h minus f of x over h. And I basically just have to apply f of x and f of x plus h to this function right here. So instead of writing, so I'm going to have the limit as h approaches 0, big fraction here, all over h. But instead of writing f of x plus h, I'm actually going to plug x plus h in for x. So I'm going to have 2 parentheses x plus h squared minus 13 parentheses x plus h plus 5. And then I'm going to subtract f of x. Well, this is f of x here, all of this stuff. So just subtract the original function, and you've got yourself a derivative. On this problem, they want us to write an expression for dy over dx, which is to say the derivative or instantaneous rate of change for this cosine squared function. So let me start by writing the general formula for instantaneous rate of change. That's the limit as h approaches 0 of f of x plus h minus f of x all over h. And basically, I just have to apply this stuff to this function up here. I don't have to plug in anything specifically for x on this one, so I'll leave x around. But now instead of writing, so I'm going to have a big fraction here, all over h. H approaches 0. But instead of writing f of x plus h, I actually have to plug x plus h into this function here. So I've now got cosine squared of x plus h plus 1 plus cosine squared, or actually, no, 1 plus x plus h squared, all over x plus h to the 4th. So we're replacing all the x's with x plus h's there, and that takes care of f of x plus h. Now we have to take care of this minus f of x business. Well, f of x is just the original function. So just stick this in a parentheses, subtract it, and call it a day.